Good morning. Waiting for a few more people to join up. All right, looks like no one's going to join, so whatever. I'm going to start. Hello, everyone. If you're here on time, thank you. I appreciate that. So I had a little change of plans. Last period, I taught the wrong lesson. But that lesson sort of stood by itself, so it's okay that I taught that one. So I'm going to teach the same one to you guys. And I've already rearranged everything so that all the quizzes are in the right order again and stuff. But I made a boo-boo last period. So basically I'm moving the lesson that I meant to do today to next week. That's okay, though. Don't worry about it. I don't even know why I'm talking about it. It's just going to confuse you unnecessarily. Okay. So what we're going to talk about today is that there are two types of waves. Okay. There are two types of waves. One type of wave is called a transverse wave. So a transverse wave is a wave in which the medium vibrates perpendicular to the direction of the wave travel. Okay? It vibrates perpendicular to the direction of wave travel. So a good example of that is so I'll give some examples. A water surface wave. Okay, why do I say that a water surface wave is a transverse wave? Well, imagine you're in a boat. You're sitting in a boat, and a water wave goes by. The water wave is going to go, water waves don't go up into the air. They stay in the surface of the water, right? So the water wave goes maybe from left to right or something like that. So the water wave is going left to right. And then what's going to happen when that wave travels underneath the boat is going to bob up and down. So you're going to kind of do this. You're going to be sitting in the boat. You're bobbing up and down. Up and down is perpendicular to left and right. Okay, so that is a transverse wave. Another example is a drum head. You hit a drum, bing. The drum head vibrates up and down like this, but the waves that were created by you hitting the drum are bouncing around between the edges of the drum. Okay, so again, that's perpendicular. The classic example of a transverse wave is an electromagnetic wave. Okay, so when I say an electromagnetic wave, that is a number of different waves that you've probably heard of before, but that includes light. Visible light is an electromagnetic wave. That includes radio waves. That includes microwaves. That includes X-rays. Includes gamma rays. So, in fact, all of these different waves, light waves, radio waves, microwaves, X-rays, they are all the same type of wave, okay? They just have different wavelengths. They're all different wavelengths of electromagnetic waves. So your eyes can't see electromagnetic waves of all wavelengths. They're not. So your eye is only sensitive to electromagnetic waves with certain wavelengths, and we call those wavelengths visible light. But it's the same type of wave as a radio wave. It's just radio waves have a wavelength that our eye is not sensitive to, okay? But it's the exact same type of wave. So, anyways, electromagnetic waves are transverse waves. So let me show you an animation of what a transverse wave looks like. Okay, here we go. So here is a transverse wave generator. So our medium in this case is this string. So a wave is being generated on the medium, and it's a little bit laggy, so it's supposed to be consistently going up and down, but it's not. And so clearly, if you were to track the peak of this wave, it's headed to the right. The wave is going out the window here. All right? The wave is going out the window. But now I want you to look at one of these green dots. Look at any one of these green dots and watch its motion as the wave travels through the medium. And what you'll see is that the green dot is moving up and down. And it's undergoing simple harmonic motion. But the point is that the green dot is moving up and down, but the wave itself is traveling from left to right. Okay? So what that means is that that is a transverse wave. Okay? So that is an example of a transverse wave. I have a nice little mnemonic to help you remember that a transverse wave vibrates perpendicular, and it goes like this. So if you look at the word transverse, it starts with a T, and if you take that T and you turn it upside down, it looks like this. And in your math class, that is the symbol for perpendicular. So that can help you remember that a transverse wave means perpendicular. Now, why do we even need a mnemonic? It's because there's another type of wave that is called a longitudinal wave. Longitudinal wave. And in a longitudinal wave, the medium vibrates parallel to the direction of wave travel. Okay? So the classic example of that is a sound wave. Sound waves are longitudinal waves. Okay? So let's go ahead and look at an animation of a longitudinal wave. Pull it up here. Okay. So what we have on the top here is the undisturbed medium. Okay. And then below that is the medium with the longitudinal wave passing through it. So I'm going to play what it looks like. And so hopefully you can see, if you look at one of these waves, like look at the green wave right here, it is moving back and forth horizontally. Okay, so the medium is being shifted horizontally, and the wave is also traveling horizontally. So those two directions are parallel to each other. So a good example of longitudinal wave is a slinky. You can think about this as like a slinky wave. Wave going down a slinky. Okay. Another thing I want to point out about longitudinal waves is that longitudinal waves actually change the density of the medium, because here we have the medium is scrunched together. And then here we have, see how this wavelength or this distance is smaller than the original distance. And then we also have places where the medium is stretched out. So here, if you look at the distance between peaks of this wave, it's greater than the distance between peaks of the undisturbed medium. Okay? So, yeah, that's it. That's what a longitudinal wave looks like when it's passing through a medium. And so I also have a mnemonic for longitudinal. Okay, so if you take the first and last letter of longitudinal, they're both L's, and you put them next to each other, it looks like that. And that is the symbol for parallel in your math class. Okay, so that's a nice little way to remember it. So when I'm drawing these waves, so if I draw a transverse wave, I will typically draw it like this. All right. If I was drawing a longitudinal wave, those are a little bit trickier to draw. Typically draw those kind of like. Put some more in here. Put one more here. Okay, that looks pretty good. Okay, so there are different parts for transverse waves and longitudinal waves. So the highest point in a transverse wave is called a crest. The lowest point in a transverse wave is called a trough. Like what a horse drinks out of. A horse drinks out of a trough. It's a divot. If you, for a longitudinal wave, the terms are a little bit different. So there are, you'll notice with longitudinal waves, there are points where the medium is scrunched up together. Uh-oh. There are points where the medium is scrunched up together, and those points are called compressions. So that is an example of a compression. And compressions take the medium and they raise the density. So the density is higher at locations of compression. So the medium has actually been pulled together and squished. So that's called a compression. And then you also have locations where the medium is stretched out. And so that is called a rarefaction. And so rarefactions have lower density. All right. So the thing about longitudinal waves is they change the density of the medium. Transverse waves do not change the density of the medium. Okay. I remember rarefaction by the fact that it has rare in it. And rare means less common. So the medium is stretched out. The medium is not as plentiful as it was before. It is rarer. Okay? That's how I remember it. But you can remember it however you want to. So what have we learned up to this point in this lesson? We've essentially learned some vocabulary terms. We've learned transverse, longitudinal. We've learned about the parts of transverse waves, their crest and trough. We've learned about the parts of longitudinal waves, compression and rarefaction. And we've learned examples of each type of wave. There are mediums that allow both types of waves. Okay. There are also mediums that only allow one type. Okay. So some examples of mediums that allow both types of waves. The Earth. The Earth's crust and the Earth's mantle. The crust of the Earth and the mantle of the Earth allow both types of waves. Okay? So typically any solid material will allow both types of waves. Another example is a slinky. All right, and I forgot to I have a bunch of slinkies in my classroom, and I wanted to grab one, but I haven't been to my classroom in months, and I don't have a slinky in my house. So, but you can imagine a slinky extending horizontally between my hands, and if I take the slinky and I go like this on one end, it's going to make a transverse wave go along the slinky, okay? If I take the slinky and I take one end and I vibrate it like this, I'm going to be creating compressions and rarefactions that will travel along the length of the slinky, so I can make a transverse wave or a longitudinal wave on a slinky. Air, the atmosphere, only allows longitudinal waves. So you will not, so sound is always going to be a longitudinal wave. All right. Water only allows longitudinal waves. It doesn't allow transverse waves. So generally speaking, fluids only allow longitudinal waves. They don't allow transverse waves. Solids will allow both. So if you have a medium that allows both, so if the medium allows both, the speed of a wave depends on the type of wave. So in other words, a transverse wave is going to travel at a different speed from a longitudinal wave. And in fact, usually, so I don't want to say always, but usually, and I can't think of any examples of the contrary, so I don't think this is an always statement. I think it probably is not an always statement, but usually the velocity of a longitudinal wave, the speed of a longitudinal wave, is greater than the speed of a transverse wave. Okay? So let's actually do an example of this. So I want to talk about earthquakes. All right? So this example is about earthquakes. All right? So let's suppose that in the Earth's crust, transverse waves travel at 1,500 meters per second, and longitudinal waves travel at, let's say, 2,200 meters per second. All right? So let's suppose an earthquake happens. All right? So when an earthquake happens, it generates all different kinds of waves. It makes transverse waves. It makes... oh, there's a good question in the chat. Can they allow both at the exact same time? Yes. And this is a perfect example of that. So an earthquake happens, the Earth's crust shifts, and it generates transverse waves, longitudinal waves sent out in every direction, okay? Now what happens is, because the longitudinal waves are faster, they pull ahead of the transverse waves, okay? So if you have a detector, a seismograph that detects seismic waves, the seismograph is going to pick up the longitudinal waves. It'll start you know how the seismograph works. It's like a piece of paper, and then there's like a pen, and it kind of jiggles, and it goes like that. It's going to start jiggling because of the longitudinal wave first. Okay, so you'll see like an initial jiggle, and then you'll get a secondary jiggle from the transverse waves. So there's a delay. The longitudinal wave arrives first, and then the transverse wave. Okay? So let's suppose that an earthquake happens, and the transverse wave arrive 4 seconds after the longitudinal wave. Okay? Based on this, so actually, if we know the properties of the Earth's crust, okay, so we know how fast these waves go, and we know the delay, we can actually calculate how far away the earthquake was. All right, and I will show you how. So remember, as long as the medium is consistent, a given wave will travel at a constant speed. So because the wave is traveling at a constant speed, the displacement is going to be speed times time. We're not going to have the plus 1/2 at squared because it's not accelerated. Okay, so this is our equation that we're going to play around with because it's a constant speed. So let's write one of these for the longitudinal wave. So the longitudinal wave travels a distance delta x. Okay, that's what we're trying to calculate, right? We're trying to calculate how far away was the wave. It travels at a speed of 2200. And let's just say that it took an amount of time t to reach us. All right? So that's our equation for the longitudinal wave. Let's try the transverse wave now. The transverse wave was generated at the same location and was detected by the same sensor, okay? So the transverse wave has the same delta x, but it has a different speed of only 1,500 meters per second. And it had a different time. Whatever amount of time the longitudinal wave took to reach the detector, the transverse wave took 4 more seconds. So it took t plus 4 seconds, because t represents the time for the longitudinal wave to reach the detector. So the transverse took that amount of time plus 4 seconds. So now what I'm going to do is, you'll notice I have 2 variables and 2 equations. So this is what's called a system of equations. Now I have delta x, those are the same. So I'm going to set delta x equal to delta x. So I have 2200t equals 1500t plus 6000. So how did that become 6000? Well, that's because I took the 1500 and I distributed it, and 1500 times 4 is 6000. Now I'm going to subtract 1500t from both sides. I get 700t equals 6000. Divide both sides by 700. I get t equals 8.6 seconds. Okay. All right. 8.6 seconds. And then I take that time and I plug it into either one of those 2 equations. All right. I'm going to plug it into the top one. So now delta x is 2200. And I know that the longitudinal wave traveled for 8.6 seconds before it reached the sensor. And so that gives 18,900 meters, so about 19 kilometers. The earthquake was about 19 kilometers away. Now here's the thing about a single detector, is that a single detector doesn't know which direction the earthquake came from. Okay? It can't detect the direction of wave travel. So what do? Well, if you just have a single sensor, okay, it knows that the earthquake happened somewhere 18,900 meters away. Okay? So you draw a circle around that detector. So this is detector 1. Okay? And we know that the earthquake happened 18,900 meters away, but we don't know which direction it came from. So it could be anywhere. The earthquake happened anywhere on this circle. But then what you do is, there's a second detector, and for the second detector, they are going to have a different amount of delay. Okay? So they're going to be able to do their own calculation and say, for me, the earthquake was only 10,000 meters away. So they'll draw their own circle. All right? And then you need that doesn't have that at the center. And then you have a third detector that does the calculation. And it deduces that the earthquake was, this far away. Okay? So you can see that the only spot that is consistent with all three detectors is if the earthquake happened right there, because that's the spot where the circles, each of these detectors knows that the earthquake happened somewhere on their own circle. So the only place that is on every circle is this location right there. So that is where the epicenter was. All right. So that, you know, if an earthquake happens and you turn on the news, they can tell you exactly where the epicenter was. And so this is how they do it. This is essentially how they know where the epicenter was. So this process is called triangulation. All right. I wanted to do a calculation involving longitudinal waves. So let's suppose we have a longitudinal wave that is traveling along the z-axis. Okay, so here is the z-axis. All right, and here is z equals 0. All right, and here is z equals 1. Okay. So what is the distance between z equals 0 and z equals 1? Well, the distance would be 1 meter. Okay. But when a wave passes through, it causes a displacement of the medium. So this point is going to get moved, and this point is going to get moved in response to the wave. Okay. So let's suppose I have a displacement of the longitudinal wave versus z. Okay. And that displacement is 0.3 cosine of z. All right. Now, because this is a longitudinal wave, we have to interpret what does the displacement mean. So a positive displacement, so if d is greater than 0, that means that the medium is displaced forward. Okay. If d is less than 0, the medium is displaced backwards, so to the left. All right. And if the displacement is 0, then that point in the medium is just not moved at all. It's important to point out that this is at a particular instant. Okay, why do I say at a particular instant? Because these displacements change. Waves do not cause a constant displacement. The amount of displacement changes as the wave passes by. Okay, so this is a displacement at a particular moment. Okay, so let's figure out how much was z equals 0 displaced. That would be d of 0. And I'm going to have my calculator in radians mode for this problem. So that would be 0.3 cosine of 0. 0 radians. Okay, and that's equal to plus 0.3. All right, plus 0.3 meters. So that means that z equals 0 is displaced forward 0.3 meters by the wave. Okay, so it's going to end up about right here. It's going to be displaced forward. So now it is at 0.3. It has been displaced forward to z equals 0.3. Let's look at this point, z equals 1. So what is the displacement of z equals 1? Well, that would be 0.3 cosine of 1 radian, which, if I plug this into my calculator, I already did this example last period, so I won't plug it in again. I know it is equal to plus 0.16 meters. So that means that this point is displaced forward by 0.16 meters. So now it is at z equals 1.16. So I added 0.16 to that. So if I want to know what is the new distance between those 2 points. So originally they were 1 meter apart, and now they are 1.16 minus 0.3. Okay, they are only 0.86 meters apart. So the wave had the effect of compressing those 2 points closer together. Notice that both points are shifted, but they were shifted by different amounts, and so the result was that they got closer. Okay, so this is how longitudinal waves work. They change the density. They squeeze points together. They pull points apart to adjust the density. All right. So the last thing I want to talk about today is a little bit more about transverse waves. If you think about transverse waves, there are 2 possibilities. Okay. Let's say I have a transverse wave that's headed directly towards the camera. Okay. That transverse wave, if it's vibrating perpendicular to the direction of wave travel, it could be vibrating up and down. So the wave goes like that. But the transverse wave has another possibility. It could also be going side to side and sort of slithering towards you. Okay? So the 2 possibilities of transverse waves are that the medium vibrates vertically, or it could vibrate horizontally. All right? And these 2 options are called polarizations. So that is an important vocabulary term, polarizations. Longitudinal waves don't have polarizations because, you know, if we have a line, there's only one direction parallel to the line. That's along the line, okay? But if you have perpendicular, there's 2 directions perpendicular to a line. So you have 2 polarizations of transverse waves, okay? So let's suppose, again, we have a wave traveling towards the camera in the z direction, okay? So a wave travels in the z direction, okay? And let's actually say 2 waves travel in the z direction, okay? At a particular moment, remember, the displacement that a wave makes depends on time because waves move. They inherently move, okay? So this is at a particular moment. There are 2 waves, and one of them is vertically polarized. So it has a vertical polarization as a function of z, and that is equal to 3 sine of 2z. okay? But then there are two waves, and the other wave is horizontally polarized. And the horizontal polarization as a function of z is 2 cosine of 3z. All right? So, and these two waves are both in the same medium. So these two waves are in a superposition. Okay? Now, if you have two waves that have the same polarization and you want to know the total displacement of those waves, you just add them together, okay? But it's a little bit more complicated when the two waves are polarized in different directions because they're causing motion in different directions, okay? So the question is, how far is z equals 1 displaced by the wave at that instant? Okay, so what I should do is I should calculate what was the vertical displacement at 1. Z equals 1 meter. And so that would be, so I would plug in z equals 1, I would get 3 sine of 2 times 1 radians, 2 times 1. And so I already did this calculation last period, so I know that it is plus 2.7 meters. Okay. Then I would do the same calculation for the horizontally polarized wave, which is going to be, it has its own displacement, 2 cosine of 3 times 1 radians, and that gives minus 2 meters. Okay? So now let's imagine that the wave is traveling directly towards you. Okay? So that's out of the page directly towards you. That's the z direction. Okay? We know that this point in the medium is displaced vertically by 2.7 meters. So it goes up 2.7. Okay? And then we know it is displaced horizontally negative 2 meters. So it moves to the left 2 meters. All right? So the combination of moving up and to the left means you're moving diagonally. So what happens is when you have two waves that are perpendicularly polarized and they're in superposition, they will displace the medium diagonally. And you can get all kinds of diagonal motion. You can get waves that spiral. That's called circular polarization, and that's a combination of up and down and side to side, but out of sync. So you go up, but then as you're coming back down, you go to the side, and so you actually spiral. Okay? So kind of like out of sync vertical and horizontal is a wave that makes a spiral. That's called elliptical polarization. If the two waves are the same size, when they combine, they can make a circularly polarized wave. So it's a perfect. But you can have waves that are polarized, or they have a bigger vertical wave than horizontal, so they might go. So the up down is bigger than the side to side. If the two waves are in sync, then when they superpose, they'll just make a diagonally polarized wave. Okay. So anyways, if we want to know how far is it displaced, well, the answer isn't 2.1 or 2. It starts out here and it ends up here. So it's this distance, which is the hypotenuse of the triangle. So we're going to use the Pythagorean theorem to get the distance at this point is displaced. because this is a right triangle. So we have square root of 2 squared plus 2.7 squared. And so z equals 1 is displaced 3.4 meters from where it was by the passage of the wave through the medium. So that's kind of neat. All right, kiddos, that's everything I have for today.